Hi everyone, we're going to be going over geometric sequences. This is our last section in chapter 6. I'd like you to write down your learning goals. We're going to identify geometric sequences and we're going to be able to write them as functions. So highlight, identify, highlight the words write functions. Okay, so now it's time that I would like you to glue in an actual definition of what a geometric sequence is. So on the left hand side, let's write in our key terms, geometric sequence and common ratio. And so I've talked to you guys a lot about common ratio, and I've been trying to preemptively discuss common ratio so that this doesn't feel like an entirely new idea to you. A geometric sequence is a ratio between each pair of terms in the sequence, and that ratio is called the common ratio. Please get out the highlighter. I'd like you to highlight the word geometric sequence, common ratio, and then I'd like you to make sure you highlight this part down here where it points to the common ratio in this sequence. And so we can see that this is a sequence by the dot, 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 indicating that it's going to continue with this pattern. And the common ratio, how we know it's geometric, is because we're multiplying by 5 in each step. 1 times 5 gives you 5, 5 times 5 gives you 25, and 25 times 5 gives you 125. And so the next term in the sequence would be 125 times 5. Example 1, identifying geometric sequences. Decide whether each sequence is arithmetic, geometric, or neither. So write down our key ideas on the left-hand side, and let's get started. So from 3 to 6, 6 to 12, 24 to 48, we need to decide whether or not it's arithmetic, geometric, or neither. Arithmetic means we're either adding or subtracting. Geometric means we're multiplying or dividing. And then neither means we have none of them. It means we're not adding, subtracting, or multiplying and dividing. And so let's dive in here on part A. How does 3 get to 6? And 6 get to 12? And so on and so forth. From 3 to 6, we can see we're multiplying by 2. We're multiplying by 2 at every step. Therefore, because we know we're multiplying, this must be a geometric sequence. We know the common ratio is the number 2. But we can simply just write geometric because we notice it's changing by multiplication. Part B, we have the sequence 12, 15, 18, 21, and it would continue going. We're not multiplying, we are adding by 3. And so when we are adding, that's under arithmetic, so this is an arithmetic sequence. Moreover, this is a linear function or linear sequence because it's adding consistently. And we would say we have a common difference. In part C, we go from 10 to 5 to 2.5 to 1.25. So we're not subtracting by 5. Instead, we're actually dividing by 2 at each of these steps. So 10 divided by 2 gives us 5. 5 divided by 2 gives us 2.5. And 2.5 divided by 2 gives us 1.25. It's another way of saying we're going from 10 to 5 by not dividing by 2, but also multiplying by 1 over 2. And so we can change that division simply to a multiplication. So our common ratio would be 1/2, and therefore this is a geometric sequence. So we can just simply say, because we know it's multiplying, we know that this sequence has to be geometric. Part D, we're going to look at this sequence from 8 to 12 to 18 to 27. And so to figure this one out, we're adding by 4, adding by 6. Okay, so we're not adding. But if you'd like to figure out how we're multiplying and it's not so obvious how to go from 8 to 12, you can take 12 and go back to 8. When you take 12 and you divide by 8, it gives you 1.5. And so we're multiplying each step by 1.5. And so because we know we're multiplying, this again means we have a geometric sequence. So let's write geometric, put a line underneath it, and then make sure we write that we are multiplying. And that is why we know it is geometric. Take a second and really pause this video and determine whether or not these 3 sequences are arithmetic, geometric, or neither. In number 1, you can see that we're subtracting by 4, and so that would tell us that this is arithmetic. Number 2, Maybe it's very difficult to see from 1024 to 128, but it's easier to see from 16 to 2 we'd be dividing by 8. And if you test it back from 1024 to 128, you do find that that is true. So this is geometric. And then part 3, we add by 4, we add by 4, and then we add by 6, which means we're not adding. If we multiply, so 2 times 3 gives you 6, but 6 times 3 does not give you 10, so this is neither. Example 2, we are going to extend geometric sequences, meaning we're going to move them forward. So let's write down our key ideas. We're extending a geometric sequence. And we're also going to establish what is R, or what is the common ratio. So our example here wants us to write the next 3 terms of each geometric sequence. So in our first sequence, I'm denoting that 3 is the first term, 6 is the second term, 12 is the third term, and 24 is the fourth term. And you'll notice we're multiplying by 2. It's a very similar sequence that we've seen in the past. And so we'll be multiplying by 2 to get to the 5th term, to the 6th term, and to the 7th term. We know R is equal to 2 because that's what we're multiplying by to change every time. It's our common ratio. Our 5th term, we would take 24 and multiply it by 2. Our 6th term would take the 5th term and multiply it by 2, and so on. So 24 times 2 gives us 48. We continue 96 and then 192. And that is how these problems go. If I ask you to write the next 3 terms, you're going to be sure to tell me what R is and then also tell me what the next 3 terms are. So I'm going to write down the names of each of the terms in our next sequence, making sure that we're trying to find A5, A6, and A7. It's just, again, the way we write the terms in a sequence. So from 64 to negative 16, and 16 to 4, and 4 to negative 1. Maybe it's difficult to see how it moves forward, but you can take 16 and divide 64, or you can take 64 and divide 16. Either way, you'll find that we are multiplying by 0.25, and because we're going from positive to negative and then negative to positive, that means we're multiplying by a negative every single time. Therefore, our common ratio is negative 0.25. So I'm going to write that in these parentheses, negative 0.25. I'm going to go ahead and set up our 5th term, 6th term, and 7th term so we can fill these out. Just know we're changing every term by multiplying by negative 0.25. So negative 1 times 0.25 gives us 0.25. 0.25 times negative 0.25 gives us the next step. And then we take that number and multiply it by negative 0.25 one final time to get an even smaller decimal. We're not going to waste any time. We're moving on to part C. So I'm going to write down the names of the terms one more time. We need to figure out how it's changing from each term in the sequence to find A5, A6, and A7. So how does it change from 1.5 to 4.5? We'll take 4.5 and divide 1.5, or take any of the further digits in the sequence and divide the prior, and you'll find the number that we're multiplying by each step. So in this example, we're multiplying by 3. Therefore, our common ratio is 3. The common ratio tells us that we are multiplying to get to further steps. So we'll take 40.5 and multiply that, by 3. That'll give us 121.5. We'll take that number, 121.5, multiply it by 3 to get 364.5, and then one more time to get 1093.5. Our last example, or part in example 2, we have a sequence that's changing from positive to negative, negative to positive. So that tells you that our common ratio is going to be a negative number once again. I'm going to set this up like we've been setting up the prior problems. I'm going to tell you all the names of the terms. Be sure to set this up so that I know what I'm looking for. We're looking for what it's changing by, and we're looking for the next 3 terms in the sequences. So from 7 to 14, we're multiplying by 2, but make sure again, because you know that it goes from positive to negative, we be sure to include the negative. Our R must be negative 2. So our 5th, 6th, and 7th term means we're multiplying the prior steps by negative 2 each time. Negative 56 times negative 2 will give us 112. 112 times negative 2 will give us negative 224. And then negative 224 times negative 2 is 448. Try this on your own. We're going to write the next three terms of this geometric sequence from 1 to 3, 3 to 9, 9 to 27. We're multiplying by 3 each time. So 27 times 3 gives us 81. 81 times 3 gives us 243. And then 243 times 3 gives us 729. We're going to do the same thing for number 7. Notice we're going from negative to positive. So we are multiplying by 2, but we're not multiplying by positive 2. We're multiplying by negative 2 each time. Therefore, 16 times negative 2 gives us negative 32. And negative 32 times negative 2 goes to positive 64. And then 64 goes to negative 128. Our last core concept in Chapter 6. I'd like you to write in Cornell-style notes, geometric sequence equation on the left. And then on this core concept, we have two new terms basically. In here we have a sub n and a1. We have a new exponent, but let's not get too stressed out. Let's imagine a table first. And let's try to compare to what we know and how to connect it to what I'm trying to teach you now. So before, I gave you a formula that looked like y equals a times b to the x power. A was where we started. So in this example, we start at 2. And notice we're multiplying by 2 each step. So b to the x would be times 2 to the x. In our new equation, a sub 1 is not when x is 0, but this time it's when x is 1, our first term, not the 0th term. Our r is still 2. We're still multiplying by 2 in each step. And so our really only big difference here is we don't need the 0th term. We need the first term. And then we just plug it into the formula that I will provide you. So earlier we would have to find the 0th term, and that would give us a. But in this example, we just need the first term. Example 3, writing equations from geometric sequences. So glue in example 3, we're going to write an equation for the nth term of the geometric sequence provided, and then we're going to find a sub 10. We're going to find the 10th term. So I'm going to start by rewriting the sequence 2, 12, 72, 432. We need to find r, and we need to find a sub 10, meaning the 10th term. So we have the first, second, third, and fourth term. To see how it changes from 2 to 12, we can take the bigger number 12 and divide 2, or 72 and divide 12. Either way, we figured out we're multiplying by 6. Each step we multiply by 6. Therefore, to find the 10th step, we just need to multiply by 6 consistently. We're writing an equation first. So we need a sub 1 and r. We can see a sub 1 is our first term, so it's 2. And we are just plugging this into the formula that I've provided in that core concept. So a sub 1 is 2, and r is 6, and everything else stays the exact same. And so if we want to find a sub 10, that's the 10th term, we just make a sub 10 equal to 2 times 6 to the 10 minus 1 power. This can be simplified. 2 times 6 to the 9th power. And this will give us 20,155,392. Part B, we're going to do the same exact thing. We just have a different sequence. And then we're going to find not the 10th term, but the 17th term. So I'm going to write a sub 1 above each term, and so on and so forth. So we know where we start. We start at 3. And we need to know how we change. So 3 to 12, 12 to 48, 48 to 192. Just take the bigger numbers and divide the smaller numbers. 12 divided by 3 gives us 4. So that means we must be multiplying by 4. And if we test it out, it does work. So we know r, and we know a sub 1. A sub 1 is 3, where we started. And r is 4, what we're multiplying by each step. We'll combine this into the formula I've taught you. A sub n is equal to a sub 1 times r to the n minus 1. So a sub n is equal to 3 times 4 to the n minus 1. And now we want to find a sub 17. So we can write a sub 17 is equal to 3 times 4 to the 17 minus 1 power. We can simplify. So we have 3 times 4 to the 16th power. And this is going to give us a pretty big number here. We're going to get 12,884,901,888. It's a big number. I'd like you to try this on your own. Write an equation for the nth term of the geometric sequence using the new formula, and then find the 9th term. So you need to find a sub 1, and you need to find r. A sub 1 is 1, where we start, and r is how we change. We're multiplying by 5, but we're going from positive to negative, so we're multiplying by negative 5. So we have r, and we have a sub 1. Let's combine them into the formula. So a sub 1 is 1, r is negative 5, so we'll fill those in. 1 times negative 5, and if it's a negative, we'll put it in parentheses. And then we need to find a sub 9. So we plug in 9 for n. So we have 1 times negative 5 to the 9 minus 1 power. That gives us 1 times negative 5 to the 8th power. So a negative multiplied by itself a positive number of times is going to give us a positive value. It'll give us 390,625.